Welcome to Pomodoro Joe for Thursday, June 29th, 2023. Today we're looking at LeetCode problem 864, shortest path to get all keys. This is a hard problem. All right, so for this one, we are given an m by n grid where dot means an empty cell, hashtag is a wall, at is the start position, a lowercase letter represents a key, and an uppercase letter represents a lock. So we start at the starting position, and each move consists of moving up, down, left, or right. You cannot walk outside the grid, and you cannot walk through walls. So we have to pay attention to our bounds and our walls. It looks like we have anywhere between 1 to 6 keys inclusive, and up to 1 to 6 locks. Okay, you can only go through a cell with a lock in it if you have the corresponding key. Now the keys are lowercase letters and the locks are uppercase letters. So we have to have a lowercase a to go through the uppercase A lock. All right, our goal is to acquire all of the keys in the shortest path possible and return that number. If it's impossible, then we return -1. All right, so this is a super tricky problem. We have some examples. So this is where we start. We can pick up this key, we can go through this lock, and then we get to this key. So it looks like that's 1, 2, 3, 4, 5, 6, 7, 8, and indeed it is 8. Now for this one, it looks like we have a couple paths. We could go down this way, but then we get blocked by this guy, so we have to come back up and go around, or we could go this way and then come back down this guy, or we could go this way and go through the lock and then down. So that looks like that's going to be our fastest path. So that's 1, 2, 3, 4, 5, 6, and indeed we get 6. All right, we have some constraints. Looks like we have a fairly small grid, which is good. All right, so we'll put 25 minutes on the Pomodoro timer and we will get started. Now this is going to require a lot of code, so I'm going to be moving pretty fast. If you don't understand, that's totally okay. A lot of this is building up on knowledge that you have to have acquired by doing other problems. So if you don't understand something in this video, make a note of what you don't understand, and then maybe go back and try to find a video that describes that piece of this puzzle. So for this, I think we will be doing a breadth first search. So essentially we'll find our starting point, we'll find all the keys and all the locks, then we'll just go through every cell we can, up, down, left, right, finding all the keys until we run out of keys to find. All right, so for this, we will have some result. We'll start it at -1 to begin with, because that's our default if we don't have an answer, and we will return our results at the end. All right, let's see. We need a couple pieces before we can even start. Like, we need to know where the start position is. So for that, I'll just start it at none. We need to know what keys we have. Now for this one, it does say we have between 1 and 6 keys, so we don't actually know how many keys we have for each map. So let's see, I'll have keys, and we'll just have a set for that. And then we'll also have locks, and we'll have a set for that. I don't know if I need both of them, but let's just grab them in case we do. What else will be useful here? Well, knowing our boundaries will be useful. So I'll have a maximum x, and that'll just be the length of our grid for row 0 -1. And I'll also have a max y, and that's just going to be the length of our grid -1. Now for this, I'll be using screen space type coordinates. So my 0, 0 will be the upper left corner, and x will get greater as we move right, and y will get greater as we go down. So 0, 0 is at the top, and y gets bigger as we go down. All right, so I have my max x and max y. Okay, now standard breadth first traversal, we'll have a queue, and we'll just put our start value in the queue. Now I'm probably going to need more than just the start value. Like, I already know that I need to keep track of how many steps we take, so I might need not just start, but I'll need the start and the steps. So we'll do that. Let's see, start and our steps will be 0. And let's make a note of what these are here. So this will be position and steps. Okay, so now we know what we're storing here. What else do we need in here? Well, we probably need to know which keys we have in our inventory. So let's have an inventory here. Now the question is, how do we represent our inventory? Now a set might be easy. A dictionary might work too. A list might work. I don't really know. So let's start with a set to begin with. So we'll have a set of keys as our inventory. All right. So we have our queue to start with, and our position, inventory, and step will be the value in each element of our queue. So standard breadth first search. While we still have something to go through, while we still have steps to take, we will go through our queue here. So while we have a queue, I'll just call this state. So we'll pop the state off the queue. Now, one thing I haven't brought up here is our visited. So typically when you do a breadth first search, you go through your grid and you keep track of which cells you've already visited so that you don't end up backtracking or going in circles. Now, the problem that we run into here is we might need to backtrack or go in circles. Well, maybe not circles, but we might need to backtrack. Let's see if there's an example. There's not really an example here. But you could certainly imagine you might have to go pick up a key. Let's say this key, we're at this space here. You might have to go pick up that key. Then once you have the key, you need to backtrack. So we'll need to keep track of this in some way. So typically you just keep track of every cell you visit. But in this case, we might need to visit the same cell more than once. So what will allow us to visit the same cell more than once? Well, that's when we change our inventory. For example, we don't want to visit the same cell multiple times on the way to get one key. But once we have a key, then we might need to backtrack. So there's this sort of change of our visited state once we get to a new key. So that's one of the pieces of this puzzle. Basically, once we find a key, we need to reset our visited state, or we need to keep track of our visited state for every state of our inventory. We'll see which one works out better for us here. Okay, so we pop our state off of the queue. So at this point, let's check our position and see if there's a key at this position. So our options at any point in time, when we get a state, we can either be on a new key, where we add that key to our inventory. We can be on a key that we've already added, so we might not need to change anything, or we can be on an empty cell. If we are on a new key and we add it to our inventory, this might be the final key in the puzzle, so we might actually need to end at this point. So let's check to see this position, what's at this position. All right, so our position is just state at index 0. What else do we have? We have our inventory, and that's going to be state index 1. And we have our steps, and that's state at index 2. So the first thing we'll check, what's at this position? Do we have a new key? Let's find out. So I'm going to have the value equal, let's do this. Just so I don't have to re-index the grid a bunch, let's do this. We'll have our value be the grid at, and that's y first and then x second, because y represents the row, which is our up and down, and x represents our column, which is our left and right. All right, so our value at yx, let's check to see if this is a key. So if the value is in our keys, now if we find a key, there's a couple options. We've already got this key, or we don't already have this key. So let's check to see if this key is in our inventory. Okay, if this key is already in our inventory, then we don't really need to do anything. We'll just continue. Oh, that's not true. We don't continue. We might need to go up, down, left, or right at this point. All right. Let's see if the key is not in the inventory. I think that's more important. If the key is not in the inventory, we'll want to add this key to our inventory and possibly reset our visited state. This is where it's going to get complicated, so let's see what we can do. First, let's add the key to our inventory. So we'll add this value to our inventory. What else do we need to do? We might need to reset our visited state. Now, if we just kept a single visited state out here at this level, if we reset our visited state, we might be resetting the visited state for all of the nodes that are in our queue, which is not something we'd want to do. Because typically, if a visited state is a set, for example, that's going to be a reference variable. And if you make a change to that reference variable, it's going to change all of the references to that reference variable. So we don't really want to reset our visited here. We could pass our visited through, basically associate a visited with every element in our queue. We could create a new visited set here, but in that case we would end up having a lot of data being duplicated across these different elements. So one way to handle this, and this is sort of the crux of the problem. One way to handle this is we'll have a visited state dictionary. Instead of having a set of visited cells, we'll have a dictionary where the key is our key state or our inventory state, and the value will be which cells we visited for that key state or inventory. So essentially what we're saying is, as we're moving through our grid, we don't want to end up backtracking, so we need to keep track of which cells we've already been to. But once we get to a key, we kind of have to wipe out that history. We don't care which cells we've been to because we might need to backtrack to go find the next key. So once we get to this key, we'll create a new visited state that just is represented, I guess, by the state of keys in our inventory. So once we reach a new key, we can essentially create a new state just for this new set of keys in our inventory. I know that's confusing, so let's just code it up and I'll see if it makes sense here. So the key will be our inventory state. And the value will be a set of visited cells. So this will be a default dictionary. And the value will be a set. Okay, so once we get to a place where we grab our key, we found a new key, this could be the end. So one thing we might want to do right here is just check, is this the final key in our list? So if the length of our inventory is equal to the length of keys, hey, we found all the keys, we're done. So at this point, our result will just be equal to steps. Okay, so our result will be equal to steps. This is a little bit interesting. At this point, we should be done. We could probably just return steps here. We might need to check to make sure that we have the minimum value. So well, because this is breadth first, we should be done. So we should be able to return steps here. We might have to revisit that if it becomes a problem. All right, so we found the final key and we're done. We return steps. If we haven't found the final key, well, then we do need to update our visited state here. So our visited for this key state, our inventory, will equal a new set, and we'll start it off with this current position. Okay, cool. Oh, but now there's another problem. This inventory is a set. We just made it easy. Hey, let's make this an inventory a set. But you cannot use a set as a key in a dictionary because a set is not a hashable value. So we can't use a set for this inventory anymore. So we need to find a new way to do this inventory. We could have an array, but the same problem with the array. You can't use an array as a key in a dictionary. What you can use a number, you can use a string, you can use, oh, I like string. Yeah, let's use a string. So we'll have a string, but that does make this more complicated. We can't just add the value here. So let's create a helper function. All right. Add key to inventory. So we'll have our inventory and we'll have this new key. So how do we add this new key? So this is ugly. We want to keep our keys in a sorted order. So our inventory, we'll just add the key to it, but then we need to sort it and return this sorted inventory. And the way we sort it, well, let's see, inventory, well, that's just going to equal, we need to create a list out of the inventory. Then we need to sort that list. So we'll do a sorted list. And then we need to convert that back into a string. So to do that, we can just use an empty string and join. Yeah, this is super ugly. Another way you could do this is you could actually use a number. You could use like an integer and have specific integers for different states, A, B, C, D, whatever keys you have. You can make it a bitmap or like a mask and mask these out. For me, I'm just going to use a string because it's easy, but it's going to be slow. And that does mean that we can't just do this add here. We need to do a add key to inventory call. So our inventory will equal add key to our inventory with this key. It looks like this should be val. This should be val. All right. So this is starting to shape up. We're going through, we've landed on a cell that has a key. We'll add that key to our inventory. If we're done, we can return. If we're not done, we sort of create a new visited set for this new starting point. We're essentially starting our search fresh from this new start point. Okay, now we get to the rest of the traversal. So regardless of whether or not this space had a key, we still need to continue traversing if we're not done. So at this point, we need to look up, down, left, and right to see if there are other spaces we can go to. So for that, I'll create some new variables here. Up. And now what's our up position? Well, we're the same x, but we're going y minus 1. Now remember, I have 0, 0 at the top, so up is going in the negative direction for y, and down is going in the positive direction for y. All right, so up is x, y minus 1, but it's only if y is greater than 0. Else, we don't have an up. So that's when we're at the boundary there. Down, very similar. We'll have x, but we'll have y plus 1. But again, only if y is less than max y. Else, none. All right. And then same thing for left and right. Now I like to take all of my directions and put them into one list so I can just loop through the list. So I'll have directions. Okay, now we can just loop through our list of directions. So for our direction in our directions. All right, first let's handle the easy cases. If we're outside the bounds, so if d is equal to none, well, there's nothing we can do. We'll just continue. What's the other easy one? Well, if we've already visited this d, so we have to check our visited for this state. So if d is in the visited for this inventory, so for this particular state, in that case, we're just going to continue. So either this direction is out of bounds, or we've already gone to that cell. We can just continue. We don't need to worry about this one. Okay, what's next? Well, let's get the value out of this cell. All right, so we've already got the value for these cells up here, but let's get our dx and dy out of this direction. All right, and let's get the grid at dx and dy. So if the grid at dx, or actually it's dy first, dx, if that is equal to this hashtag, that means we're at a wall, so we have to continue. We can't go in that direction. So we've handled out of bounds, we've handled visited, and we've handled walls. What about locks? All right, let's check to see if that, let me just maybe get the value out here again. I'll call it cell value so it doesn't clash with our other value. All right. So if our cell value is a wall, we have to continue. What if it's in our locks? What if this is a lock cell? So if cell val is in locks, okay, now we've got a lock. The question is, do we have the key? All right, let's see. Maybe we'll have another helper function here. Well, basically we want to know if we can't unlock this lock. Maybe we'll do this. If not, can unlock. And we'll pass in the cell value, the lock. And we'll pass in our inventory, because we have to know if we have the key to unlock this lock. So if we cannot unlock this lock, then we'll continue. So these are all the cases where we can't actually go to this direction. All right, so we still need to create this function. So let's just grab this now so we don't forget. Put this up here with our other helper. All right, I'm gonna pass for now. We'll come back to that. All right, now we've gotten to a direction we can actually step in. So let's add this to our queue so we actually traverse in this direction, and we'll also have to update our visited list. All right, so queue, we will append. Let's see, what's in our queue? We've got, where's my list here? All right, position, inventory, and steps. So the position, well, that's just D. Our inventory hasn't changed. And our steps, well, we've taken one more step, so it gets increased by 1. And now we have to put this direction into our visited list here. So our visited for this inventory, we will add this D. All right, looking pretty good. Oh, we're down to 3 minutes. So let's implement this guy up here, can unlock. All right, we have to know if we can unlock this cell. All right, if this cell is a lock, we have to have the key in our inventory. I'm just gonna do this super simply. So we'll return, let's see, we'll have cell val to lower, or lowercase, in inventory. Now that's pretty cheesy, I admit, but hopefully that works. Okay, let's see if this works. We're so low on time, I just want to run this really quick and see if it works. Default dict, misspelled. Let's try this. All right. All right, I didn't pull X and Y out of my position. Let's do that here. I just realized we also didn't have our start position yet. All right, so we haven't gone through and found our start position. Oh man, so many things to do. Okay, let's find our start position down. Where do we do it? Let's do it here. Find the start. We also haven't found our keys. Oh wow, for every X in range. We're gonna run out of time on this one. For every X in range, max X, and for every Y in range, max Y. And since I already subtracted 1 for each of these, I need to add 1 back when we do this traversal. All right, the value will just be the grid at this Y and X. All right. And if the value is equal to at, this is the start, then our start is going to be equal to this X and Y. Else if the value is in, let's see, A, B, C, D, E, F, they're up to 6. Then this will be a key. So keys.add val. All right, val is in A, B, C, D. Oh no, I'm just gonna push through. We're so close. So then we have a lock. Okay, so now we have our start position. Did I call it start or start position? There we go. We have our start position, we have our keys, we have our lock. Locks, plural. All right, give this one more shot. Let's say we have start here. We'll go through, we should find the start. But I created this after my queue, nuts. So we have to do this before we create our queue. So let's do this whole thing. Right after we do our max X, let me do this. All right. Order is important. So once we create our max x and y, then we can find our start, and then we can use it in our queue. Man, so many things. Right, this should be wrapped in a tuple. Cell val is not defined because this is cell val, not call val. Man. Result is not defined. Didn't I define result? Okay, so that works. Oh man, that is ugly, but it works. Okay, so we have a working solution. Let's submit this and see if we can pass. And we pass. All right, we do okay. We beat 59% for runtime and 93% for memory. Holy smokes, we do awesome for memory. All right, one quick thing that we can do that might speed this up. So over here, I'm using our standard list as my queue. So this queue right now is just standard Python list. Now these are not particularly efficient. Yeah, these are not particularly efficient for popping things in and out of. However, a deck, which stands for double-ended queue, is really efficient for popping things in and out, or pushing things in, popping them out. So we will use a deck, that is D-E-Q-U-E. Basically, we just wrap our list, our initial list, in this deck constructor. We'll keep this queue, and instead of saying pop 0, we have to say pop left. Now, this basically does the same thing as our list was doing, just should be a little bit more efficient at doing it. Let's see if this helps. And it helps, a little bit. Now we're at 66% for runtime, 95% for memory, so let's see, we gain about 6 or 7% runtime, and we actually get a little gain in memory as well. So hey, not too bad. All right. So I know this is a rushed one, this was fast, but there's a lot to go through with this problem. I recommend watch this video again, go back and jump in and try this one out. Once again, this is LeetCode problem 864, shortest path to get all keys. Check it out, see if you can do this on your own. If you have trouble, you can always come back and watch this video again. All right, that is it for me. I hope you enjoyed this, hope you had fun, hope you learned something, hope you can go out and write better code.